Thanks for coming, everybody. I hope this will be informative. So this presentation was actually spurred off of, in reality, it was a Chief Delphi post that I put up probably 3 or 4 months ago that just had a bunch of pictures and context and kind of showed a little bit about the design process that 1678 goes through to go from a concept of a prototype. So starting at the very beginning of the season, when we come up with a subsystem that we think we need on the robot, and we go through the prototyping stage and then the actual like finished development of it. So we'll talk a little bit about the full cycle of it from start to finish, and I'll show you a lot of pictures and actually really add a lot of context and pictures and videos to show what actually happens on 1678. So just a little background on who we are. So my name is Dave Powers. I'm an engineering manager at a company called Advanced Farm Technologies. We make robots that pick apples and strawberries and then do automated pack lines to pack those strawberries. So it's pretty cool. It's a startup. Me and a bunch of citrus mentors work there. Mike's the director of hardware. Matt and Zach both work there with me. And then I think we've had about a dozen citrus kids go through the program, the internship program. Brendan was one of them. So this is and on Citrus, I'm a hardware and design mentor, and I primarily focus on subsystem development and then training the drivers, do a lot of driver practice stuff. So pretty in-depth. This is my 14th year in FRC, so big robots, and this is my 22nd year in FIRST. My dad started a team in 1998, so I kind of grew up with it. So I have a lot of background in that, maybe a little too much, seen a lot of robots. So. And then, Brendan, you can talk a little bit about who you are.
My name is Brendan Rockwell. I'm the design lead for Team 1678. So on the team, I'm basically in charge of the entire robot's development and assembly. So starting with prototyping early on, and then moving into CAD to get our alpha robot out, and then working on our beta, and then hopefully comp robots. This is my 3rd year in FRC. And I'm supposed to say the most important thing I learned.
Yeah, one of the questions, I'm going to ask a couple of the other Citrus kids questions, kind of when we go throughout the process. But one of the first ones I want to ask is, what is one of the most important things you think you've learned in FRC over the course of your 3 years here?
So over the 3 years, basically, the first thing I would say I learned is just working in a more professional setting. Before FRC, we really, in my school, don't have a lot of true, do a thing really well clubs as much, so it's nice to have that. And then also probably a lot of just how to design things, so starting at a prototyping, assembly, that kind of thing.
Awesome. Yeah, and I really encourage as we go through, ask questions as we go, because this will be a lot better if it's interactive, and as you see things that come up, there's a lot of context that, I tried to add as many pictures and stuff, but sometimes we will gloss over a step that will unfortunately seem obvious to me because I was there in the moment, but might not seem obvious to all of you. So point it out, ask questions. The more questions you ask, the more you will all get out of it. So don't be afraid to ask questions as we go. Does anybody have any questions on that? Yeah. Say my dad started Team 228, a team out of Meriden, Connecticut, and they're still going. So they've been around for a while. Yeah, it was fun. I got a fun picture I'll show you, y'all, when I was Champs used to be in Epcot every year in Disney World in the early 2000s. So I got some cool pictures of me when we were younger. So I talked a little bit about it, but just to add a little more context. So we're going to do a pretty in-depth case study on the hopper of the 1678 2022 robot. So I was a really big fan of this subsystem because I think it tied in a lot of so something as simple as a hopper, right? Most teams have a hopper in some capacity this year. So how could we take the simple hopper and kind of take it to the next level, right? So you'll see us go through the process in this case study of we take a regular simple hopper that's based off of a 2020 robot, and we actually add a little bit more details to it and then simplify it in the process. And I'll talk a little bit more about the things that we pulled out of it and the failures that we had along the way, which I think is important to emphasize, because a lot of the times I think you see some of the bigger teams, you just see the end robot, but you don't get to see all of the failures that they go through all of the process. It takes many iterations of this, and the hopper is kind of a good example of that, where there were a lot of different steps that it took to get something that ended up just being like 2 motors and 3 sets of star wheels, and it gave us a bunch of capability. And then I'll share some tips and tricks on how you can speed up your design process. So Citrus, yeah, go ahead. Yeah, so I'll explain that in the next one, talk a little bit, the next slide. So so I'll share some tips and tricks just on how to speed up the design process. So this past year, during the build season, before we got to our first event, Citrus built 4 separate robots. So we built an alpha robot, a beta robot, an epsilon robot, and then the competition robot, which you all saw at our week 1 event. So the development process on Citrus is super accelerated. And I'll talk a little bit about how we accomplish that and the things that we kind of learned, the tips, the tricks that enable us to do that and sort of utilize all of the students that we have in the team, because Citrus is a pretty big team. And then I'll just share a bunch of personal stuff, pictures and videos from over the course of the season, and y'all can ask questions on it. So some more context for you. So a hopper. So in this context for this game, the hopper is in this robot. We'll just talk about this subsystem. So ignore the shooter that's on the top of it, and then you can ignore the singulator from the front. So this omni wheel up there. So the hopper in this context is just where we store the game pieces for this year. So when we were going into deciding what we wanted to do with the game, it seemed pretty simple, right? You just need some way to store the game pieces so that you can queue them up to the scoring. But we really wanted to try and push it a little bit and set some design requirements for ourselves. So just some of the major high-level design requirements that we had that were developed throughout the course of the season that changed from the beginning of the season, which I'll show you in a second, is we wanted this to be a dual-use hopper. So we wanted it to not only store the balls, but we wanted it to be able to sort the balls. So if you watch the Citrus robot, it does a really good job of very quickly being able to drive into a group of a bunch of different color balls, and it comes out with the 2 balls that we need, the 2 game pieces that are our alliance color, and it'll automatically do that. So we wanted something that was able to do both the game piece storage and the sorting, and we wanted it to be completely automated. So we knew we needed to add some sensors and technology and some automation to that. We wanted it to be simple and reliable, which are 2 core principles of all of our design processes. Citrus over the years has had some kind of crazy complex robots. The 2020 Spinodexer, for the students that were there, can probably nod to the complexity of that system and how long it took. And sort of as we go throughout the season or throughout the years, there's been a big push to try and make the robots have the same level of capability, but try and make them simpler. Can one of the Citrus kids grab me a bottle of water from somewhere? I don't know if somebody can grab me one. I appreciate that. So really, how did we? This is the final competition hopper that we ended with. So how did we get there? So where did we start? So this picture is way back. It's actually, is that day 1 or day 2?
Day 1.
Day 1. So day 1 of build season, right? We get the game. Everybody gets the game. It's released. The set of rules are released, and then we develop our own game rules test that goes out. And then all of the students are required for the first half of the day to learn as much as they can about the game and get as much context, know as deeply as much as they can before they kind of get to that point where we even start thinking about the game. Like, we don't care really how we're going to do anything. We just want to be able to figure out all of the things that we need to do, which I think is a core principle in figuring out when you're going to develop a subsystem. You really need to learn what the challenge is and what the scope of the challenge is, and kind of all of the pieces that are going to that you're going to need to think about. So within the rules and the context of the system. Can you grab that, Brendan? Thanks. All the rules in the context of the system, and you're kind of going to be able to get a really good outline of what is capable and what isn't allowed, right? So we knew that, like, you could only hold 2 game pieces this year. So that goes into the context that you build when you're going through your process of fleshing out what you think the robot capabilities could do. So then when us as a team, Citrus, we kind of come together once everybody has a good understanding of the rules, and we just make a list of the things that we think the robot should do. Not how they do it, We don't think about subsystems. We don't think about independent subsystems, or we don't think about, oh, like climbers start developing like, oh, the 254 climb in 2013 looked awesome for this year. Like, we don't think about any of that. It's literally just listing all of the things that the robot should do. The robot can do this. It will do this year. So this is a picture of some of the things that we kind of came to as a conclusion of the team. And I like to show this because it really paints a cool picture to see where we started at the beginning of the season and then where we end up specifically in the storage portion of it. So obviously we had the score the game pieces. So we knew we wanted to score in the upper goal because it was worth more than scoring it in the low goal. We thought that we were going to have to score in both of the goals potentially. We wanted to be able to drive quickly around the field. We knew we wanted to intake the game pieces off of the ground. We knew we wanted to potentially spit the balls back out the intake. So that was the first thing that we thought about, like, okay, when we have the game pieces, not how is it going to do it, but it needs to be able to take the game piece in, but it also needs to remove that out. So in theory, right, you think you just, okay, run the motors in the other direction. It's pretty simple. And then for the storage, which is the important things, we knew we wanted to hold 2 game pieces. And we also had written down hold the game pieces while we were climbing. And when I was making this presentation, I was like, why in the world did we want to do that? And it occurred to me, we wanted to do that because we thought that there was going to be a lot of teams that were going to not climb and just spend some of the time out there scoring the balls. And there was a lot of teams kind of at the mid upper level that would, they would do like a really quick mid or a high climb, but spend the last 30 to 15 seconds just scoring the ball. So we wanted to be able to remove some of those from the context of the game. And then we talk about the climb. We wanted to make sure that we had the traverse climb vision. We decided pretty early we wanted to do swerve. Over the last 2 years, I think we built 8 swerve robots.
Over the last 2 years, we've built a total of 6 swerve bots, starting with basically, if you saw us at last Madtown, we had 3 there, and we also built 1 more for 2019 off-season. So at that point, basically all of our programmers were way more comfortable with swerve than they were with tank, which is fairly obvious because it's basically all they'd worked with, and then also all of our designers way much preferred swerve because basically it gives you the entire center of the robot much more access because you can access like the sides and you don't have to worry about going over chain and stuff like that.
Yeah, and just a small caveat, Citrus is very lucky we have a lot of resources to be able to do stuff like that, but I think it's important to note that not every team can go out and build that many swerve drives before they get an attempt at it. But the really important portion of it was we just wanted to give ourselves the experience to be able to confidently say, okay, if we put this on the competition robot, it isn't going to prevent us from reaching that ceiling. We aren't going to spend the bulk and majority of 75% of our build season putting an effort into trying to do a swerve. We wanted to make it something simple in concept and be able to move through the motions of it. And that really was enabled by doing all of that practice at the beginning. Trying to think if there was anything else. Cool. So, okay, now that we have this list of context, I'm going to talk a little bit more about the next step in the process. So now that we know what we want to do, we're going to think about how we want to do it, right? So in this one, we have our design requirements. We want to hold those game pieces, and that's really the big thing, and then a little bit on the sorting. So when Citrus as a whole starts thinking about different subsystems or how we're going to build a robot, a lot of it goes back to just thinking about the very first thing that it seems that we always fall towards is going back to the history books and looking at games from the past. What can we learn from robots that have already existed and already excelled in those games and transfer that knowledge and maybe modify it a little bit over to this year's game? So a big thing is we really use our brains and we scour the internet and watch a lot of it. So like this year's game, right, was very similar to 2020. So thankfully that was a couple of years ago. There was a pretty big knowledge base of the robots around there, but we watched a lot of matches. We went on the Blue Alliance and we looked at different robots and we got suggestions and we really made a list of all of the robots that kind of like had a subsystem that hit those goals that we wanted to accomplish. So storing the balls and potentially sorting them or having some type of automation. And really the important part with this is you're just using this as a blueprint to build the lowest effort first prototype that you can possibly get to see how the game pieces interact with both each other and in a subsystem, right? So the context of this is you really want to make sure that you're just getting a better understanding throughout the entire thing of we know how the game pieces will interact with different wheels, like different size wheels, different gear ratios, we're really trying to apply all of that context so we can understand how everything's interacting with each other, so it'll give us a better understanding and we can see the failure points and we can kind of move forward with all of that. So once we've done a bunch of research on past robots, the team actually does a bunch of sketching. And I think this is kind of one of the most fun portions of it from my point of view. So these are just 3 pictures from the second day of build season. So one of the coolest exercises that the team does, in my mind, is every student on the team. It doesn't matter the subsystem. They're all sitting together and they're really taking a moment to like draw out some of their ideas, mostly based on robots that have already existed in the past. But they're trying to get the context of like, okay, how can I design a full system that really like captures all of those design requirements that we have. So here you can see Mike on the microphone yelling as he normally does. Like everybody kind of knows Mike and how chaotic he is in real life. He's like that all the time. You know, I work with him on both this and work, so he's enthusiastic about everything. So he's really encouraging all the students to try things. So you see students in the background sketching on the whiteboard. We got some of the students sketching on grid paper, and then this picture is actually a picture of Brendan. And do you want to? I kind of wanted to bring you up to talk a little bit about the context of how you and your team maybe came to the conclusion that you thought this was a good idea.
Yeah. And
feel free to be very candid and like.
Sure.
Yeah.
So, in case you can't really see because it's very blurry, this is basically, if you guys are familiar,
973's robot from 2020.
it's just that. To be honest, me and then the guy on the right, left-hand side, the ginger, was our previous design lead. It's the easiest way to describe him.
Candid, not offensive.
We had both kind of been talking about how to do ball games previously, and we both kind of arrived on if Citrus wants to build simple robots instead of overly complex ones, 973 was by far the best example of that in 2020. Like, if you remember, they could do one thing, but they could do it better than anyone else in the world. So, like, if you watch Chezzy, they were basically going over the middle of the field, and defense basically didn't affect them because they would just drive through them, and they would basically just score, and they would just cycle back and forth over and over, and they would just get insane amounts of points compared to us, who, even though we had, like, a way more complicated robot, we're still essentially doing the same back and forth cycle, but slower, and it was less accurate also a lot of the time. So, basically, we were like, hey, if 973 can do this really simple concept in, like, honestly, they have a relatively small team compared to ours, so they can do it with like less resources. We should try to do something similar to that, at least for alpha, because it basically gives us a launch point for where we should go, because it's clearly successful in past games, and it's basically something we can work with easily. So both of us kind of came to the same robot, except I think the only difference of opinion was where the intake would face. So I think my design had intake facing with the shooter, and then his design had it the other way around, where we were kind of debating on which way would be more beneficial.
Yeah, and I think it's kind of a cool context because in 2021, when did Chezzy happen? 2021 for the 2020 game. So we built this swerve turret complicated Mark II version of our 2020 robot and put a bunch of effort into it. And then we thought we were going to be hot stuff, and we put a bunch of practice into it. And then we went to Chezzy Champs, and we just sat there scanning our hood scan the turret. Like, I'm sure if any of you have turrets, you're familiar with you just trying to lock onto the goal, and you would just hear everybody sitting in the stands yelling like hood scan, like trying to convince them to like somehow will the robot to lock on. And then while we were doing that, we had one match with 973. I think they did triple the amount of cycles that we did, and they have a fixed hood, no turret, and they were a tank drive, the complete opposite of what we had. Crazy spin it Xer.
They also just took their 2020 robot and they're like, yeah, we just tested it out and brought it out. This is the first time they turned it on.
Yeah, and they like, very minimal programming control on their shooter. I think they was just running open loop or something crazy. Like the context of what they were able to do with something so simple, I think really inspired us this year to push the limits, starting with the Alpha Robot, design something simple and just see how the game interacts. So I kind of pictured, so if anybody hasn't seen the robot, this is the 973 2020 robot. So you can see, just like Brendan's drawing, it has the intake that pivots down. It just has a bottom floor that rotates. So this is just some polycord on the bottom, and it'll travel up this indexer, the hopper, right? So mainly in the concept of the context of this presentation, you'll see that some of our prototypes that formed out of this for the Hopper subteam really formed out of like this picture and looking at that geometry and stuff. But when we took Brendan's drawing and some pictures of this, kind of the next step that you really want to accomplish is just try and rip a prototype of it as quickly as possible, like immediately. I know it sounds kind of obvious, like as quickly as you can, but like before you even think, so you have a concept, just build it. And you're going to learn more about that concept and you will get farther in the design. I promise you, if you spend the time building it and interacting with it, than you will if you spend your time like actually just talking about it and trying to feather out the details in the design. And you're going to build, and the nice part about ripping these quick prototypes is you're immediately getting hands-on with the game pieces, like I said, and you can build as many of them as you want. So our subsystems and our teams kind of, once the sketching and the drawing is done, they will continue with those groups, kind of get split up into sub teams and stuff, and then they'll just start cranking on low effort, quick turn prototypes. And I'll show some pictures and some videos of that. So this is actually, so after we got that, I think this was day 3 of build season.
Day 4.
Day 4 of build season, where we had our first prototype of the tower that of the 973 2020 concept. So you can see in these videos, here, I'll just put them on loop so I can talk while they go. So you can see these are two iterations of it. This one on my right is the very first iteration of it, and you can see this prototype is nothing more than like 4 pieces of wood. It's 2 pieces of plywood and then a couple 2x4s, and then we just drilled some holes and ran some shafts through it, and they're controlling it with a drill. So this concept is like ultra critical to just learning dimensions, learning how the stuff interacts with different wheel materials. You can see we're using the orange polycarb, which is what 973 did. So we directly copied from them just to see how it interact with the game piece. And it's like the game piece this year was a little different than the 2020 game piece, so there was a little doubts. And you can kind of see I like to point out some of the failures on these. So we learn really quickly that if you want to get good usage out of this, you really need to be spinning it as quickly as possible. But then you can see there's, in some instances, you see how it kind of hangs up down here, and the student has to like give it a little bit of an effort to push it up till it actually catches. So, okay, what did we just learn? We just learned a couple key things, right? Like we know we need to do something to support this in the bottom of the prototype so that we can get the ball to engage with the polycord rollers all the way through the system. So then we take that information, and this was probably hours later, we just add on a couple more pieces of wood, and similar to the 973 robot, we throw some powered rollers on the bottom. And then you can see how it's not complicated. This is literally just rolls of tape that are taped onto the shafts. And all of this stuff is giving us even more context and getting us a little bit closer to the next step. So in this one, a couple examples of the things we learned on this, right, is you can see now, okay, we have some of the bottom rollers, but the ball is still getting stuck at the bottom, right? So, okay, what do we learn? We learned that we're starting to think about geometry stuff now. How can we enclose that so we can better capture the ball all the way through the system? We kind of had a hint at it by there, but we didn't know the full context of the spacing, so we just needed to take a stab at it, make an attempt at it.
I think another really important thing to talk about for basically all of our mechanisms this year was how essential it was to figure out what compression we wanted to use on the game piece. So basically, from like day one, we all felt the ball like all pumped up, and it was like, wow, feels really hard. It probably won't bend a lot. But then as each subsystem like started testing out what they wanted to do, we realized really quickly, wait, no, we want to put a lot of compression on this because otherwise half the time it will just sit there like it's a dead spot. So for instance, on the indexer, you saw that thing where it was just sitting at the bottom. There were 2 pulleys touching that. Like, it wasn't that it was there. We just learned, okay, we need to force it in more. We need to make sure that it's going up. We need to make sure that basically all of those things are pushing in. Another example on the shooter, we started thinking about half an inch. We ended up going to 3 times that. And on the intake, I think we thought we would just need, like, tangent basically to it. And we ended up having to put about ½ inch to 1 inch compression on the entire subsystem.
And just another note that kind of came into this is you can see the ball gets stuck down here. So one of the other learning points is maybe we need something at the front that helps push the ball through the system. So you'll see in this next slide, if I figure out how to full screen.
You can do it, Dave.
I'm still learning this PowerPoint thing. So now you can see some of the failure points that we were just talking about, right? So we figured out how to get proper C2C. So as we were going through those, there's probably a couple more pictures of them that I just didn't have because this stuff is happening so quickly, where they're adjusting the C2C being the center to center, so how far away those pulleys are from each other. They're really adjusting those dimensions to see how it best engages with the polycord as it goes through the system. And then another big thing was, like I mentioned earlier, that front roller that's really going to pull the ball into the system and pull the game piece through the indexers. So how long do you think that was the transition between those prototypes and this?
Yeah, sure. So
mock-up?
this indexer was put together day 6 of build season.
Yeah, so then you can see now at this point we have a good understanding of all of our critical dimensions. We have a good understanding of how the game piece is going to interact with polycord, how the game piece is going to interact with maybe 3D printed pulleys, how it's going to interact with the different feeds and speeds that we're going to run through the system. Okay, we build that context in our head, and then at this point, we are hitting the CAD, and we're going to open up our on-shape model, and we're going to start doing some 2D sketching to confirm those dimensions. And I wish I had some stuff, some more like models of this, but I would say that so ignoring the game piece shooter, which is just placed on top of it, this bottom portion of it is basically exactly the same thing as in this this context, right, or this prototype. It's just a little more refined, right? So we have our at this point we're using a little bit nicer pieces of plywood. This stuff gets laser cut. We're gonna add additional motors to the system, so we're actually gonna put stuff on they're powered by Falcons. And at this point, we're starting to think in our context, we really like to take our advanced prototypes and kind of put them in line with some of the other prototypes that are in the system. And that's a cool context, right? So this above the indexer, right, is one of our shooter prototypes. So we just took one of those and you plop it on top, and then you can start seeing even more in depth how it's running through the system. But this it may look kind of complex, and I wish I had a picture of the hopper together, but it's no more complex than something like this when it comes to you're just really taking all of these dimensions. You did all the hard work already, right? Like there's nothing more than just going into a 2D sketch in Onshape, which is something, there's plenty of resources out there going through the fundamentals in the Onshape learning program. We use Onshape, so I talk about Onshape, or Onshape, Inventor, SolidWorks, whatever you use. There's plenty of resources to be able to sketch a 2D model of those critical dimensions, so you can build then a little bit more advanced of a prototype, right, that has just to verify the dimensions and all of the different bits of it a little bit further. So at the end of week 1, basically, we have now all of the context we need to build a hopper, and we start thinking about how we can integrate it with the system a little bit. And since we have those early sketches of full robot, we kind of know our design constraints and how big and stuff. So that really helps us add context to the whole system. So then we can take this subsystem and we can actually just start testing with it. I think the biggest, most underrated thing that people like are missing on this stuff is really you got to like understand a few different things. So in the context of something like this prototype, right, you really need to push it as far as you can so you can learn the limits of the system and you can kind of learn the abilities of it, and you can kind of learn how it's going to interact with some of the other stuff. So it's really hard to know what your limits are without actually putting it through all of its paces. So we probably ran, now that we have this prototype, we probably run, hundreds, if not thousands of balls through the system, of game pieces through the system. And we're just kind of seeing how things are interacting with each other. We're, again, just writing down all the failure points. And you really need to make sure that you're supporting yourself in the discovery process of this. Like, the longer you take, within reason, right? Don't spend all 6 weeks running balls through your subsystem to learn. Like, there's a limit. You'll understand. You'll kind of get to the point and you're like, okay, we figured it out. But you really need to support yourself in discovery and give yourself enough time to learn all of those kind of like pinch points and what it's capable of. And then you need to make a list of the reasons of why it's good. And then the one that's pretty hard that I think, even we struggle with is why it's bad. I think in the real world, the good can be a little bit of a given, and the bad is the really important context that you need to give yourself, because that'll help you get to the next step, the next version of it. And as you're doing those, all of those cycles and running it through the system, you're really learning what the upper limit of, even if you make it out of metal now, or you make it out of polycarb, like it's going to be your final version of it, what's going to be your upper ceiling of this. And you can kind of get a better context of like, okay, is this within the scope that we're reaching for? Or do we need additional context to try and bring it to the next level? So, and in this context, now you're kind of going to see I wish I had some videos of the alpha robot driving around, but basically we had taken this prototype and we just dropped it on a chassis. And then I think some of you probably, I don't know how published it was, but we ended up getting a 5-ball auto out of these prototypes together. So our reach goal for autos for the year, we were able to do within 9 days of build season, using all of those concepts throughout all of our subsystems, right? So we had built the drivetrain really easily. We had the shooter prototype. We had a intake prototype. We had the hopper prototype. And those are kind of all the bits and pieces that went together. So now you kind of see, as you're forming your team to develop these processes, and as you're kind of going through, you're really just taking like a group of students and you're putting them on each one of these, and you're letting them go through this design cycle a few times. And you're letting them figure out the context and the limits and everything. And then once you get all the systems together, you can do a system-wide evaluation, and you really want to be running it as much as you possibly can. So in this context, right, then we have this beautiful prototype. We understand our limits, right? This hits both of our goals of what we want to do, but then something kind of occurs to us. We're like, the sorting portion of it. It's like, okay, what are our options with this prototype? It's like, okay, you intake a bad ball, a bad game piece. You either spit out the top or you spit it back out the front. It's like, okay, those are kind of two good things, but they could be slow. There's some limitations to it. The tech could be kind of hard to get it implemented. Or what if the right game piece is in one area and you want it to be in the other? And if you're going into, so say if you have a ball, you have a game piece at the top of the indexer and you intake a wrong ball, but then you got two of your good game pieces in front of you, you don't want to spit that ball back out, right? Because you're going to bowl those game pieces away, and it's going to cause you issues. So we start thinking about those limitations of the scope of that, and we start thinking, how can we mitigate that? And as it's kind of missed a little bit in the context of the whiteboard drawings and the sketches and all of that. But we kind of had, just from building this robot, these prototypes together and driving them around, it started to become very apparent that this game was likely going to be won at a high level, not by the scoring of it, because from the prototypes you kind of learn it's not easy to get the ball in the goal, but that might not be the hardest or the most time-consuming portion of it. It's probably going to be actually going and getting the game pieces, right? So where can we start shaving time and shaving effort off of those cycles? And one of the big things that we realized is like, okay, we really need to optimize for something that's going to be able to we're never going to have to worry about it. And then you can start seeing where we start, like those design requirements that I listed at the front, you can kind of really see where all of those start to bubble up with the automating it and being able to sort properly and being able to do all of that, all of those bits and pieces. So then we had this like crazy moment where we're sitting at work one day, and Matt and I, you weren't with us yet. So Matt and I and Mike, we work. So just to paint a little bit of a picture, Advanced Farm, where we all work, we work in a barn, like a really crappy old barn, because we're a startup and we don't want to spend any money. And then our offices are actually a greenhouse inside of the barn, and the greenhouse is like AC'd. So we're all sitting in there having a meeting when it's like a normal day, and we kind of get finished up talking about work stuff, and then Avery, who is a Citrus alum and came to work for AFT on the Apple team, he's not directly involved with the team at that point. He's just he's an engineer. He loves his time with Citrus. He enjoys it. So we're just talking about the game, and he's like, this kind of reminds me of something, right? It's like, this kind of reminds me of the Vex game from 2021. And we're talking to him about some of the limitations of the robot and where we want to optimize it. And he's like, I know exactly what you got to do. So he pulls up this video, and this thing kind of bubbles up, right? So right there, do you see it? It happens quick. They intake the wrong game piece, and it just goes straight through. Sorry, I don't know how the freaking thing works. Sorry, I just got really excited because it was such like a turning point moment for us in the season. So, behold, the first pooper, as we like to informally call it, the first pooper concept. And really in this moment, it was like it occurred to us that we could take something simple like a hopper and we could really use it to optimize to the next level. And we could use this as an opportunity and a tool, very simple system, right? It's just the ball is just passing through instead of going up. It's like, how hard could that be, right? So we're kind of looking at this and we're understanding the concept and maybe some of the constraints of it, and we're like, we got to test it. Like, at the least, we got to build a prototype of this to see if this is something that we can do. So the video is actually really good. You should go watch the So next, what the heck? Okay. So next we get to the point of where we have that final prototype that's on our alpha robot. It has pretty good capability, but we know there's more that we can draw out of this subsystem, right? So it's time to build a better one. So we're re-scoping of what we think this mechanism should be capable of, and we're kind of, okay, now it's time to build one that's a little more solid. It's integrated a little bit better to the system, and it has more capability. In our context, we ended up building it to be part of our beta robot, which I'll show in a second, but it doesn't need to be. You can just go through that process again of building an individual prototype subsystem, and we kind of do in this context. And then you need to make it good enough. This one needs to last hours, right? So now that you're getting a little deeper into the process, you're probably getting closer to wanting to punch one out for a competition robot. You need to start thinking about the rigidity of the system and how it's all going to integrate, and how are we going to make this so that we can actually put it through its paces and practice for its hours, not minutes. It's really hard to get a conceptual understanding of something that you're building without putting it through its paces. So this is the version 3 of the Hopper prototype. God darn it. I am just whiffing today with these. So I'm going to mute it because I'm like, we were so hyped up on seeing that Vex video that I think I called an extra meeting and some of the kids came in. And this is our first pooper prototype. So this is a video of the first concept of it. So you can see it's not far off from our original hopper design, right? Like our first hopper prototype looks pretty similar to this with the two pieces of plywood, and then you have the drills on the side. And we just added one feature, right? So you have your one in lieu of the polycord, which we knew there was going to be some issues with from our first version of it. Oh, tragic. Give me 30 seconds. So I'm going to try and do this while still talking. So now that we've added this context of this, we're going to add this one little bit in the back, which turns out is a simple little flap that you don't even need to power it, because you don't need to power the flap, because the flap, depending on which way you're running the subsystem, it'll flip up or down. And then we can just prototype this pooper concept. We can prototype how it's going to interact with each other, and we can see, is this something that's feasible, right? Is this something that's going to be something we can build into a better. Sorry, can't believe I let that happen. So you can see it's working pretty well, right? It's run through the paces. We've kind of give it a good enough shake. Again, we run it for basically hours at this point. The kids probably, like Brendan can attest, it gets kind of grueling doing these tests, but it's important to understand the limitations of the concepts of it, and the limitations of it. So we're now at this point, we have all of our limitations of it. We have all of our geometries that we need. So what are we going to do? If I can figure out how to get it to YouTube. We're going to build a better one, an even better one. So this one now, we're jumping from that wooden platform, and since I mentioned that this is in the context that we were putting together our beta robot, but it doesn't need to be that, we're actually going to build a metal version of this that's going to have the concepts baked in. So we realized when we were doing our testing, we did actually need to power the flap. So we put it on some pneumatics, so we are able to trigger it either open and the ball will pass through, or close and the ball will pass all the way up. And I don't remember what week this would have been.
This was probably around week 2.
Yeah, so probably by the end of week 2, we're probably cooking on this and cutting this stuff on the routers. So Citrus are very lucky because they have a bunch of routers in-house, so we kind of go through the process. But most of this is built out of some scrap stuff. Like these were old 2x1s, and a lot of this stuff, all the shafts and stuff were not really custom made. We had them from existing prototypes and projects. So this is just some assembly pictures. We got the Falcons all lined up so they can put it together. They got the flap on there. There's Archie just inspecting everybody's work to make sure that it's good. And then you can see we actually integrated the shooter prototype into this version of it, because we knew we wanted to build a beta version of it. So moving forward, here's a couple other pictures. So you can see this is the whole beta robot together, which again, context doesn't need to be you don't need to do that to be able to get all the context out of it. But we really wanted to do it because it would give us the ability to test it like really, really, really well. So you can see basically it's really hard to see, but you got the little flap up there that's pneumatically actuated. And then at that point we have this assembly together, and the only thing, what's the obvious next thing you need to do? You need to test it, you need to practice with it. And it's hours, not minutes. I know I keep saying this, and it's like you really, really need to push as far as you can. And now we're getting to the point of where we want to start simulating closer match environments in the context. So if you have an independent subsystem, it's a little hard to do, but it's not impossible. Like you can take, if it's just a hopper, or say if you have your intake in just a hopper, you can just put it on an unpowered drive base, or like even a moving dolly, and you can roll it across the floor, and you can start picking up balls and simulating like you're driving around, right? And that's adding a lot of more, you're getting a much deeper understanding of how it's actually going to interact with once you get into the field environment. So you really want to do your best to simulate the real things with your subsystems when you're that you think you're going to see in the match. And yeah, go for it.
About how many hours do you think Citrus put into hopper testing?
Oh God, like just actually like the prototype testing, including the beta robot, like dozens of hours probably at this point. And then this is, we're doing our best to simulate a real match. So this is we got in the truck and we drove down to the 254 practice shop. They're normally pretty good with letting people come in and practice. And we're just picking up some balls and we're going through the paces and we're kind of learning the things that it's going to limit. But you can do all of this manually. Like I said, you put it on a moving dolly, you pick up some balls, you run some stuff through it. You just got to give yourself more context of it. And that video is live on, it's on YouTube, so you can go through and watch it. My YouTube channel has a bunch of different things. And then the big thing is like push it until you break it. You want to know where the failure points are. Pushing it to the point of where it breaks isn't a bad thing. It's a good thing, because so then you can learn what breaks so you can alleviate that for the future. You have a question? What was the question? Sorry, I can't hear you. Like how many prototype versions of it? So at this point, this is just the third full version of the hopper prototype. And we'll probably, before the end of the competition, before we get to the competition robot, we'll push it to probably 4 more thorough ones. Yeah? Yeah, so that's a great question. So just to add a little bit more concept, we're kind of, as we go through these processes or these cycles of come up with the concept, build a low-grade prototype, and then build a better one, we're kind of sussing out and removing the ones that are not meeting requirements. And it's as you go, like that conceptual wooden prototypes, right? You could build 10 of those if you wanted. Like it's very low effort, so it gives you the ability to kind of go through the whole process and test every single one. So you're not wondering like 6 weeks down the road, you're like, man, I wish we tested that other one, and you live the rest of your life thinking about like, man, what if I had like a half spinodexer instead of full spin? Like just test it, and use the beginning of the season to run those super low effort prototypes. And don't be afraid to continue doing that through the course of the year. So you'll see like the citrus intake changes drastically from the beta robot to the epsilon robot, was literally scrapped essentially. And I'm kind of going to go into this. I might go a couple minutes over, so I'm sorry about that. But I'll try and go through. So now that we have all that context with the beta robot, what are we thinking now? We sit back, we get back to the shop, and we got to be really honest with ourselves, right? And it's not easy, right? So we knew that this beta robot, when we were building the beta robot, we did not know that was not going to be the citrus competition robot. We thought we were just like, man, we hit the nail on the head, like all of this stuff's going to work. But then when we got down to the poof shop, we started running it. We were like, we could do better. We could definitely do better. We can get more out of this. So what are some of the things we can get more out of? I will learn how to do this before the end of the concept, before the end of the presentation. So we really evaluated all of the issues, and you got to remember through the entire thing, failure is learning. Failure isn't a failure in any sense of the context, as long as you're learning from it through the entire process. Really, that's like if there's one thing you take out of this, is as you're going through the prototyping and building your subsystems, like the failing is not learning, it is just teaching you the things that don't make sense for this concept, so you're going to move on and do something different. And don't be afraid to scrap it and start over. So to apply a little bit of context to this, right, I was talking about the powered flap in the back. So this is a slow-mo video. So we built this whole subsystem, right? And then we start adding software onto it where we know we have a color sensor. And this is probably, some of this stuff is a little more complicated, so it gets kind of tough to, it doesn't need to be this complicated. But in this context, we added a color sensor and a couple beam breaks. And we were really just looking at like testing the concept of, as we run that ball through the hopper, is the flap even fast enough? The first time we run it, we're like, oh God, oh no, we just put all of this effort into development. The flap, there's no way we're going to get this flap to open up fast enough for a ball to pass through before you can see right here, right? The ball engages with the color sensor right up here in this little slot. And the latency on that color sensor is actually so steep that by the time it triggers the pistons, it's like, that's like milliseconds, right? A couple dozen milliseconds or something. But that's too long, and the flap it's not going to open. We're taking these slow-mo videos, and we're like, we're going to move on. It's not going to work. Like, it's not going to hit the design requirements. We built this entire beta robot. Probably time to scrap it. And that's a really hard thing to admit to yourself, but it's important to be able to do that if you want to like continue to succeed. But it's also important for the context. I say that, but it's also important to remember that at some point, and I'll talk about this a little on the next version of it, like, is it good enough? It's good enough. Like, you got to decide at that point within your team's capabilities of what is good enough. So at this point, we're going to adapt and overcome. We're really going to push for a different solution. So the concept that we moved from the flap didn't work. What else can we try? At this point, we were talking about doing a couple different concepts and versions of it. At this point, we were thinking a little bit more about that Vex robot. And that Vex robot didn't have a flap or anything. It was just the way that the wheels in the indexer were turning were determining where the ball was going to go, the path that the ball was going to go. So we ripped up like literally the simplest of prototypes, right? This is 3 holes drilled in a piece of wood with 3 drills. And just like look at this. This is starting to give us the context of like, okay, now we know that we can divert the ball using these star wheels. It's like, okay, now we're kind of onto something, right? We don't have to worry about a flap. The latency, by the time the ball gets through there, we should be able to determine the direction that motor's spinning because it's a lot quicker of a mechanism than the pneumatics are. And it's really going to give us maybe a little bit closer to what we're looking for. So now it's kind of going through the cycle again. You see this, right? So we built a low effort prototype. Now what are we going to do next? We're going to build a little bit better of one. So we built a sheet metal version of it. And the sheet metal version of it is, again, instead of 2 pieces of wood, we wanted to build one that we knew we could do extensive testing on. We built it out of sheet metal. And if you look, it's pretty much the exact same one as the wood one, right? Just instead of the flap is there, we added those star wheels. So we can change the direction of the star wheels. And we could see if that concept of like storing one up there and then switching the direction of this, so we see it's wrong. We're not even doing any logic or sensor, like we're just doing this by hand. We can spit the ball out. Concept's sort of proven, right? We're like, okay, yeah, now we're getting there. Now we're getting close. So this is when everybody kind of starts getting excited. And then at this point, we're like, can we do a little bit more? And as we were testing that, of course, you're going to come up with your limitations. There were certain limitations and spot points that you're going to hit that you weren't going to totally get that subsystem to be perfect, right? Perfect like does not exist in the concept of FRC or really anything. So we asked ourselves, is it good enough? It's good enough. It's going to accomplish all of the goals that we want. It's going to push the limits of what we're capable of in terms of running software. It's simple. It's reliable. It ticks those 2 boxes at the beginning. So let's put it in a full subsystem. So I didn't want to go too in depth of the actual mechanism building of Epsilon version of it, but it's basically the exact same thing as comp. Like you'll see this is like, this isn't anything that's crazy. It's just a formula that Citrus has developed over the years of like testing low effort testing, build one a little bit better, then test it in a high fidelity concept. And then at this point we have the star wheel concept and all of the dimensions from our testing, and the students in about 2 weeks time were able to put together Epsilon. And this is some of our first testing of the color logic. And you can see it's picking up and storing the blue ones, and you see the limitations. There's still some hang-ups in there, which we kind of fuzz out with some of iterations of some other subsystems. But at this point now, we're grabbing all of the blue balls, and the red ones are just leaving the system. we've kind of accomplished the goal here, right? So it's really nothing when you break. So something that the path of getting something like this is, a lot of people just see this end product, right? And they think that like, oh, they came up with a simple concept or something. Like, no, it's really just, you need to go through the motions and learn everything you possibly can to put yourself in a position to be able to make those discoveries. Like, none of the Citrus students or mentors are any smarter than any of y'all. It's just a system that Citrus has developed. And I think that it's just like, all of you can do it. And it's really important to just understand that it's just self-evaluation and being able to just be honest with yourself, and then pushing it to the next level and kind of running through all of that. So for us, for Citrus, we kind of always are developing, right? So as you saw in that video that we had, there was a bunch of hang-ups. The ball wasn't completely draining into the hopper clearly, so we're just going to continue our development. So there's no reason to stop the entire season. There's no bag. You can keep going through this cycle. You can do this as many times as you want until the end of the year, right? You get your first event, hopefully you do well. Maybe you qualify for champs or something. You can just keep practicing. The cycle goes on as far as you want to push it. And it's really important to like strike that balance with your team and understand where the limit is. But it's just practice. And as you practice, these cycles will get significantly faster, right? The reason that Citrus can turn around these robots so much is because at this point, the team has done this hundreds of times, right? Hundreds of times. It's just practice. It's just work. It's literally just work. You don't need to think that deep about it. And the only bit that is really important is, well, it's not the only bit that's really important, but is one of the most important parts is, so Citrus has a lot of capabilities. So if you're on a smaller team, you need to make sure that you're prioritizing what cycles you're doing at any given time. So say you have a design team that's only a few people and you're kind of individually doing these design cycles, like focus really intensely on one subsystem and getting it to that point. And then you see where your next weakest link is, and then you kind of restart that process and push yourself. The kids and I joke about Kobe Bryant all the time because he's one of the personal heroes of mine in his work ethic. And he has this really funny quote about, there's like an old Nike commercial or something about him saying to Kanye's like, I'm the best. And he's like, what is it?
Are you the same animal but a different beast?
Yeah,
Dave?
are you same
mean
animal
that?
but the different beast? And I truly don't understand it. But some of the other stuff that Kobe said, it actually makes sense. And once you know what the failure feels like, determination chases success. So don't let those failures kind of be a sticking point for you. Make sure you push through. Make sure you do the cycle. You do your homework. You make some low effort. Use some low effort prototypes. You build them a little bit better. You do some testing, and you'll kind of run through all of those efforts. So I know that was a ton of information, and I kind of glossed over it. I probably should have stopped for some questions, but this picture also was in the Citrus template slides that they sent me, so I just left them. I didn't pick this. But does anybody have any final questions? Yeah.
I wanted to ask earlier, but I forgot to. When testing out for the card, do you think it's best to figure out the shooter intake mechanism before like installing like any like drive, and so that way you can test out like, oh, does Swerve drive work the best for this one, or does West Coast drive work the best?
Yeah, that's a good question. So say in the context of your testing and intake, right? Like you can simulate with the cart those different subsystems, and you can kind of go through the process. Like, right, if you have a dolly that has 4 independently castering wheels, right, you can treat it like it would be a tank drive, but then you could treat it like it's a swerve drive and come at it on an angle. And maybe you do both of those to get a deeper context before you make that other decision. And you can kind of see how you can tweak and better understand of the capabilities of all of these different prototypes by putting them in different scenarios. Did that kind of answer your question?
Yeah.
Yeah. Yeah, you can turn on the lights. Somebody want to turn them on? Yeah.
So for something with more moving parts, like a climber, where it doesn't necessarily make sense to make a prototype out of wood,
Mhm.
but also making a metal prototype could take like a while to machine. Do you have any advice about like the middle ground?
Oh God, I'm gonna
got it.
unplug my thing really quick, and I'm gonna talk while I find this.
Dave, I can just explain.
So we do build them out of wood. Like we built
Well-
our first concept for the climber out of wood.
Yeah, I think you can also, a really easy way is depending on the climber, a lot of it, there are cost solutions that you can take advantage of, or like basic designs you can take advantage of. For instance, Zach used to work at West Coast Products. They have a really great line of products or stuff like that. For example, our shooter prototypes and our climber prototypes are both based heavily off of the grade system that they run. So, for example, if you're trying to test, like, for example, our gas shot climber, you can really just take, like, their basic idea of how to do a climber and just put that on your own robot and basically see how that goes. And then you can use that as an idea. And then also for our shooter, they have, like, a system where they can, test compressions. So a lot of the answer is look to what's already been done for how to, like, come up with designs, basically. So you have to spend a lot less time for that. And then as Dave was saying, we also do a lot of our testing even with, like, really shabby quality of stuff with like our first climber prototype for a skip climb was done with a bunch of 2x4 that we screwed together and then slowly would try to spin all the way up. And then for our first gas shot
Oh,
test,
God.
it was the And then for the gas shot climber, our first test was putting it on our 4414 clone drive chassis,
Can you hit the lights really
weighing
quick?
it down with a bunch of batteries, and basically just seeing do we think this could work.
So
Dave.
which cable?
There you go.
There you go. So you're talking about a climber concept. So people that are familiar with 125 on the East Coast, they had this crazy skip climb concept, where it's basically you grab the front bar and then you're using these two, we call them the chopsticks or the tubifers, that pivoted off this middle rail, and then you had a set of arms up there that grabbed the back half of it. So we were like, okay, where do we start with this? So we literally ripped together this, it's a little more intense than two pieces of wood and some 2x4s, but it's really not that much more complicated. It took a lot longer to put it together, but it helped us test some of the geometries just, because you can unscrew an arm and screw it in over there, and then you can kind of just test it, and then you can see we're actually prototyping this concept, with a low fidelity prototype. And yeah, there you go. I forgot that happened, but that's a good example. So then we realized, like, okay, maybe we should build one that's a little bit better.
And the metal one did the same thing. Too, so.
Yeah, I don't want to show that because it was dangerous.
Threw the metal one in the trash.
Yeah. Does anybody have any other questions? You can turn the light on. Yeah.
I just had a question about the software you said you were chatting with.
Mhm.
I haven't used that one. We always use Fusion 360. I was curious why you use that software. Is there, for the students, is that making a better choice?
Sure. So basically, like in comparison, Onshape to most other CAD softwares, it's basically Google Docs. So like, it's really useful for us because in terms of what it requires to run, like we can run on school Chromebooks that they give out, like basically pretty low, grade computers can run it pretty well. So it's really great for us in that respect, where pretty much all of our students can guaranteed run Onshape. It's also really great because Onshape, you can work at it you don't have to use a desktop in the shop. You can do it at home in your bed with your laptop and your cup of cocoa if you want. It's really easy to just sit. Well, I wouldn't because I fell asleep when I did that. But overall, it's just a way easier thing to use, especially for us, where we try to do everything that we can at home. So basically, a lot of the design stuff that you saw there was done at home, or when we weren't at the shop, because basically shop time is a limited thing for us. So try to make sure that the most you can get done at home you are. So Onshape really just hit the best quality for
Yeah,
that.
it's like a cloud-based one. Go ahead.
As a mentor, it's really nice to review designs live as they're happening. The kids are working at hours that we're at work. And luckily my boss
That's not good for you guys.
lets us look at Onshape.
Yeah.
So, while the kids are working 3 o'clock or so when they get out of school, we can also be on Onshape section and give your feedback.
Yeah, we have a folder with Fusion where I can go and look, but you're saying it's more like live.
It's live.
Yeah, you can literally click on their icon and watch them CAD in real time, which they hate.
It's
But-
really
You
nerve-wracking
can send
to.
messages in live. Nope, not that. Nope, dimension. That should be a little bit long.
You're right. I do that later.
Yeah. Yeah, no, I think that Onshape is kind of a growing tool in the FRC space. They also have a ton of resources for really starting out students, beginning students.
Okay.
The fundamentals courses have been really critical for
The
us.
first time I heard of it, it was a class at MIT, and
Yeah.
they were using that, and I was like, never even heard of this program.
Yeah, so the PTC just bought Onshape, but Onshape was started by some SolidWorks alumni, some of the people that started SolidWorks. So they spun it to build the product that they thought, was of the future, which is a cloud-based program. That's great. I laugh at the kids because sometimes there was it's Felipe who did our intake on the robot. We were at Port Unimi, our week 1 event, and take it easy. And the thanks for coming. And the intake exploded, and he's like, "Oh no!" And then Mike, and I kind of talked about what he needed to improve on it. And then there's an app on his phone. He's catting on his phone, sitting in the stands, and I'm like, "Bro, you can wait till you get home at least to the hotel." But it does, it has a lot of cool capabilities for stuff like that. Yeah.
I was wondering why, is there a certain reason why you decided to scrap your flap design entirely rather than trying to spend time to fix it?
Yeah, so that's a really important question, right? Because you're always kind of up against, like, when do I spend more time on this versus when do I just abandon it and move forward? And the sunk cost fallacy, where you're really just like, okay, we literally built an entire beta robot around this concept. Like, ton of geometry effort went into, both that flap and the climber that you saw, the wooden version of the climber. Like, that beta robot was supposed to have that 125 climb on it. And we really got to the point where when you're testing it, it sometimes becomes apparent and it sometimes doesn't. And it's really up to you to understand and think really deeply about, okay, what are the capabilities of this? Maybe it's just a sensor. Maybe it's a sensor sourcing thing. We can find another sensor that has lower latency or something that is going to move a little bit faster. But we knew as we were watching the balls run through, it's like, okay, those pistons at their max PSI that we can get on this robot are not going to open fast enough, and the amount of time that it takes from the ball to pass through that sensor to when it gets past the flap, right? So we were like, we got to abandon it and we got to move on to something different. And the climber was actually pretty intense because we put all of that effort into doing the climber, and that one was pretty apparent because the metal one also exploded. Thanks so much for coming.
It was like the first time we tested and tore a 1x1 in half.
Yeah. So, okay, next question.
I just wanted to say that one reason why we use on-chip is because the student edition is free.
Yeah, it's also free.
Fusion is too.
Yeah.
But I understand watching them work.
Yeah. Any other questions? I don't know if I want your question. Okay.
Big J, what do
This is
you
going to
got?
determine whether or not you're walking home.
So when you said you want to make a list of like what works good and what's not good,
We're wrapping up.
we've got 5 minutes until everybody has to leave.
Okay, we'll be out of here in 5 minutes.
But when you're making the list of what's good and what's not good, do you think it's better to take after that take what's good and make it like 100% works 100% of the time, or take what's bad and make it decent?
Wow, that's a great question. That's such a good question.
I'm so proud of you, Dave.
Wow, how do I answer that?
You want me to?
Okay, so yeah, you want to take an attempt at it while I think of an answer?
Yeah, sure.
Make it
So,
short-winded.
I mean, a lot of it depends on what the mechanism does, right? So, for example, on the hopper, the thing it did bad was its job. So we were kind of like, well, that's
That's a great way to put it.
gotta go. But like, for example, on the shooter, what it was kind of rough at was accuracy with the like wheels when we first added them. So we were like, okay, its accuracy dropped from like 95% to like 75%, but we're getting like almost no bounce outs, which is why we switched the wheels. So at a certain point, you got to weigh the costs of like the new design versus that. And also, when something's like 99%, just leave it most of the time.
Yeah, 90% even.
90%
And I
is
think
fine.
it's also important to remember that I totally forgot what I was just about to say to you.
To quote a guy who worked at Skunkworks, the like 95% of your effort will be getting from like 98% to 100, and at FRC we don't have all that time.
Yeah.
So just send it.
I remembered. It's a lot about also you'll get better at that as you go, so don't be afraid to just make a decision and stick with it and move forward, because you'll later in life realize the context of like, oh, that was a dumb idea, we probably should have pursued it a little bit more, and you give yourself that context to not make that dumb decision next time. So
Always.